Thank you very much for inviting me to speak at this conference. So as you can hear, probably my voice is not so normal, but I hope with a microphone so it will be okay. So Hedwig instructed me to give a very elementary talk. I'll do my best. So the first part, I'll talk about some elementary number theory. So I will fix some polynomial in n variables, and let's take it over the integers. Then I can consider it also over the rationals and the complex numbers as I like. Okay. We're interested in some finite aspects of number theory, namely the following. I fix also some positive integer, and I'm interested in the solutions of f congruent to 0 mod m. So number of solutions of congruences. So where are my solutions living? My solutions are living in these finite rings, right? Z over mz to the power n. That's my solution space. So I just count. So these, I'm interested in the solutions and I want just to count them. See how this depends on m when f is fixed. And as you probably know, by the Chinese remainder theorem, it's enough to study this when m is a power of a prime. If you know these numbers of solutions for all powers of primes, well, you know them for all m. That's an easy application of the Chinese remainder theorem in number theory. So enough when m is a power of a prime. Okay, so let me fix some notation. So I will fix a prime. Okay, not very original, I'll call it P. Let's fix it. And I will denote by big Mi the number of solutions mod P to the I. Number of solutions of f congruent to 0 mod P to the I. Of course, in Z over P to the I Z to the N. Yeah. Okay. And well, there are some very natural questions. Is there some decent behavior of the MI? That's the question. If there's some, what is a decent behavior? Well, is there some regularity when I gets big? Well, you have some nice formula in terms of I. Maybe that's optimistic, but maybe the most important question is you have a countable sequence of MI. Is this sequence determined by the first that many numbers? Yeah? If you know a finite number of them, do you know all of them? Okay, let me show you some baby example of this. Okay, I'll try to focus this thing just a moment. Okay. Well, it's not optimal, but I hope you can read it. First, a very, very baby example. Two variables, y minus x squared. Of course, you know the mi from scratch because you can choose x. You have p to the I possibilities for x, and x determines y. So, and then second example. Yeah, recall first that m1 is always number of solutions of something mod p. So m1 is always counting solution over a finite field. Yeah, so indeed there you have two lines intersecting in one point. So it will be 2p minus 1. Okay, and then it's not so difficult. You have some spare time this afternoon, so you can solve the exercise of example 2. So this is the formula for mi. It's not so difficult. Okay. It becomes more interesting when you look at the, well, the standard example in singularity theory. Y squared minus x cubed. Again, m1 is easy. This is a standard parameterization of the cusp. Yeah? So you have p possible values of the parameter. So you have p solutions over the finite field with p elements. But then, well, okay, well, you can compute, you can continue computing, and well, the formulas seem to vary a bit. Yeah, so it's not a very clear formula in terms of I as in the previous example, but okay. But there, you see there is some regularity. Okay, so typically, okay, let me maybe continue here because I will show you a couple of other slides, and then I will stick to the blackboard. So when looking at these kind of questions, well, there are several possible definitions, but we put all these numbers in a formal power series, yeah, and then you try to prove something about this power series. So let me take the following convention. I will sum the mi, and then I take p to the minus nt to the I. That's just a renormalization factor, just the habit to use this, it's not important. Okay. So when you put all these numbers in a generating sequence, you hope, well, that this sequence tells you something about the numbers. So let me show this again on the slide. So again, I just repeat here the definition. And, well, there's an old conjecture, it's solved now, well, it's solved already for a long time, Motivic and Chavarji saying that this series is rational. If you think about it, saying that this series is rational, well, this implies that it's determined by a finite number of data. Yeah? You have only finite number of coefficients in the numerator and denominator, so the whole series is determined by a finite number of data. And that was the most important question about this sequence of numbers. So it's nice. It's a very nice behavior because this series is rational. Let me just quickly show you some examples. That was the parabola example. Well, okay. You can easily, it's just a geometric series if you put this in a power series. The second one is again easy. Maybe it's interesting to look at the third one. So the third one, well, the sequence of numbers, there was some, well, nice behavior, but it's hard to pin down what it was at first sight, but that's the point. Here you can summarize what's happening with the mi in this concrete form of this formal power series. That's the rational function expression. Okay, I said number theory. Of course, this is about number theory, but I'm making pictures. As you have guessed probably, why is this third one more complicated? Well, because this is already the first non-obvious singularity for curves, yeah, the cusp. Yeah. The first one was non-singular. The second one, well, was almost non-singular, just normal crossings. And this is the first non-obvious singularity. And that's the reason why it's more complicated. That, well, I hope to convince you during this talk that that's the reason. Okay. Maybe let me show you a more complicated one. Okay. So again, well, from geometric point of view, an example with just one Puiseux pair. Okay, I just claim that this is the the formal power series written in rational function form. So there will be some very complicated denominator. No, sorry, very complicated numerator, but a kind of easy denominator, just 2 factors. Yeah. And okay, the specialist in singularities will probably recognize the 18 and 65. It has something to do with the invariance of this curve. But that's for the people knowing that. So when you go back to the original problem, what, besides the fact that it's rational, is of course very interesting, because it means that this countable sequence of mi is determined by only finitely many of them. But it also says, for example, yeah, this 18 and 65 tells you something about the lim sup of these numbers to the 1 over I. And maybe just look at the last line. It gives you a non-obvious upper bound for the mi. Mi is bounded by some constant, independent of I, and then this power of p.
Did Igusa propose a formula, a closed form for this rational?
No. Maybe if I have time I come to that. Igusa proved this without giving a closed formula. Later on the Neff gave a closed formula. Igusa proved it. I will tell a few words about Igusa's idea, how he proved it. Okay, so maybe yeah, I switch off this thing now. Okay, let's go back to Blackboard. Oops. Let me tell you some words about Igusa's idea how to prove this. Well, it's quite interesting. Oh, maybe that's true. Before going on, I was also instructed to give some open problems. So let me first give you an open problem. Or maybe I can write the open problem on the side, then you can remember it. Okay. We looked at this number of solutions over these finite rings, z over p to the I z. Now I will replace z over p to the I z by fpt divided by t to the I. Yeah? These are often the things you want to compare in number theory. Yeah? I guess you had some introduction to jets yesterday, maybe of the complex numbers, I don't know. But these are kind of jets, but then over fp instead of over the complex numbers. Yeah? Instead of looking for solutions, still imagine that your polynomial is over the integer, then you can consider it over everything. Instead of counting number of solutions over this ring, count number of solutions over this finite ring. Yeah? And then similar definition of pt, of this generating functions, former power series. Is this rational? We don't know. And when I tell you the idea of Igusa's proof, in the case upstairs, well, you will maybe understand why we don't know. Yeah? Hmm? Ah, very good. Very good. Thank you. Thank you, Dimitri. Okay. What's the idea of Igusa, how he attacked the problem? Well, first, he's making the link between, so now we're back to the situation above. He's linking this power series to a p-adic integral. Okay. Let me write it down first. I integrate over p-adic integers to the n. Remember that f is over the integers, so I can consider it over the p-adic integers also. I take the p-adic norm to some parameter s. This is the Haar measure on p-adic numbers to the n. Even if you're well, not so familiar with p-adic numbers, well, it doesn't matter too much. I will give this the name z s. So what is this? It's an integral. Okay, p-adic absolute value of f. This is some positive number. You do this to the power s, and what is s? S is a complex number with real part of s positive. This is in order to make the integral converge. This thing is compact, so it's nice. You don't have. And this is nowadays called, for example, Igusa Zeta function, or Igusa Zeta function, or p-adic Igusa Zeta function. Let me just call it Igusa Zeta function of f. Yeah. Okay, what does this mean? Well, this means it's almost that. Of course, I can never remember the exact relation, but if you know this, and the other way around. So what is the exact relation? Let me write it down. If you take the series p and you substitute p to the minus s, this will be equal to p to the minus s, this p-adic integral, minus 1 divided by p to the minus s minus 1. Well, if you know one of them, you know the other one. Okay. That's the first part. And then he will in fact prove that this is a rational function in p to the minus s. Yeah? And once you have that this as a function of s is a rational in p to the minus s, well, you will have that the original series is rational in t. Yeah? Okay. Okay, I said, well, you can consider this for any s with real part of s positive. And in fact, in that region, it's important to know that this function is in fact holomorphic in S. In that region of the complex plane, it's a holomorphic function. Okay. Okay. Okay, second, so now you have an integral. I can do all kind of tricks to study integrals. Okay, if you know p-adics, it's good. If you don't really are comfortable with p-adics, it doesn't matter. Just think about integrals. You know, this is a complicated function probably. Yeah, but what one way to try to compute complicated integrals is to have a change of variables formula. Do something nice. So use change of variables formula for integrals. Formula for integrals to obtain well, an integral of something easy to obtain, but locally, not globally, but locally, an integral of monomial. That's and well, some of you have experience with that. This is where singularities pop up. You can achieve this by using embedded resolution of singularities, one of the main achievements in singularity theory. Yeah, so use embedded resolution of singularities. Embedded resolution of singularities. So okay, my f is living here. Yeah, but this is some. Okay, I wrote down p-adic integers. So in particular, you can consider the p-adic numbers. But anyway, let me write it down geometrically. I'm looking at the hypersurface f equals 0 in affine space, let's say over p-adic numbers. Yeah? And I want embedded resolution of this inclusion. Yeah? Yeah? So I want some nice space y, and then some normal cross-section divisor. I will, for the moment, not go into details. That should be an embedded resolution, meaning that the inverse image of the pullback of f, of the function f, will be locally monomial. And when you have something locally monomial, it's easy to compute, and you will see that it's rational in p to the minus s. That's Igusa's proof. He computes local contributions on this space. Yeah, of course, there's a Jacobian popping up when we use the change of variables. Yeah? But since everything becomes monomial, it's easy, and he really shows that at the end you have sum of local contributions that are all rational functions in p to the minus s. Okay.
So he controls the behavior of T under blow-up?
P is fixed for the moment.
No, of this integral or whatever. Yeah, of the integral.
You control this under blow-up.
No, the integral over f.
Yeah.
If you replace f by the blow-up, then that's what you mean under.
That's what I mean, yeah.
It's a birational change of variance.
Yeah, you replace this affine space by some other smooth manifold. You take the pullback of f, and that will be locally monomial, and then you can compute. That's his idea. Of course, you need resolution of singularities in order. Okay. All right. Okay, let me write down some corollary. So corollary, of course, is that then Pt is rational in T. And another corollary from the proof is that this function in the complex variable s, holomorphic in this part of the complex plane, has a meromorphic continuation to C. Has meromorphic continuation to C. I will use the same notation for this continuation. So on the other side of the complex plane, it can have poles. They will turn out to be very interesting. Okay. Alright, I'm going to the second part, because the conference is about Artin approximation and singularity theory. I will not talk about Artin approximation, but we'll talk about, well, I already talked about singularities. Now, link, well, a more explicit link with geometry, but it's rather differential topology. In fact, this will be the open problem too. This is a so-called monodromy conjecture. Let me first state it and then try to explain a bit what it is. Okay, I'm in the same setting, still this f over the integers, this rational function now pt, or the p-adic integral Igusa Zeta function. You can state it for pt or for zs. I will state it for zs, that's how people do it normally. Okay, I will state it for the integral. So I told you it has a meromorphic continuation, so it can have poles. So if some complex number is a pole of this, well, this meromorphic continuation of z. Maybe I should have mentioned something. Excuse me, I should have mentioned this. It has a meromorphic continuation. It's a byproduct of Igusa's proof. Another byproduct of Igusa's proof, when you look at the local contributions, it turns out that poles, the possible poles, are very special. It turns out that their real part, the poles, have real part in the negative rational numbers. That's just a byproduct of the proof, of the local computations. And this is important for the statement of the conjecture. So the conjecture says, if some complex number is a pole, so in particular if it is a pole, it must have real part a negative rational number, then you take e to the 2 pi I, this complex number. This will be a root of unity. Is a monodromy eigenvalue at some monodromy eigenvalue of f of f at some point of the hypersurface f equals 0.
It's a real formula.
Ah, thank you very much. Very good about giving elementary talks that the older people in the audience can correct me. They know this already. Thank you. Okay. So I'm not sure. So not everybody knows monodromy, or okay. But in that case, I need to get this stuff down again. So let me tell you on some picture quickly for the people who don't know it, the idea of monodromy. Is it correct that these buttons don't work simultaneously?
You can use your hand.
Ah. Thank you for the hint. Okay. So, very quick, some picture about monodromy. So I have to adjust this thing again. Okay. Then again, it is very dangerous to present this in an elementary way because there are a lot of specialists in the room. Okay, so f was over the integers, but as I told you, I can then, it has the advantage that you can consider f over everything. Now I'm consider f over the complex numbers as a function from Cn to C. Yeah? This is hypersurface f equals 0. I take some point on it. You may imagine that P is a singular point, otherwise it's not so interesting. Yeah? So it maps to the origin of C. Now I take a small ball around with the usual distance in Cn, small ball around this point, b epsilon. And then I choose a point t here very, very close to the origin. Even I choose some circle around the origin and take some point t on it, but really close to the origin. And okay, the inverse image is here, f equal t, but I intersect it immediately with the ball. Yeah, this is a so-called Milnor fiber, local Milnor fiber, ft. So the inverse image of t intersected with the ball. I can take another one on the same circle. This will be ft prime. And the point is that ft, that all for all the numbers here on this circle, all these ft's, ft primes, ft double primes, they are all diffeomorphic. Yeah? Okay, this is not really functioning well. And in fact, you can induce this diffeomorphism by making a loop around this circle. Yeah, you start with t, you go to t prime, you go back to t, and at the end you have a diffeomorphism from ft to itself called monodromy. You have to take care. In fact, it's not really well defined. It's well defined up to homotopy, but it doesn't matter. We will take a homology anyway, and then it's well defined independent of any choices. If you take homology or cohomology, and then I consider homology or cohomology with coefficients in C. Then I have C vector spaces. I have well, the transformation of these finite dimensional vector spaces, and well, the eigenvalues of these linear maps, these are precisely called monodromy eigenvalues of f in P. Okay, I don't want to dwell too long on that. It just, if you never saw it before, that's the framework. It's really differential topology, a really geometric invariance of f at P. And in order to maybe compare with the last example, yeah. So that was maybe the most complicated example. So I showed you the rational function pt for this example, but then if you translate pt to zs, it was almost the same. I recall that if you describe it in zs, these were the real parts of the poles, -1 and -18/65. This is what I claimed, yeah. And okay, it's not so easy to compute monodromy eigenvalues when the singularity is not isolated, but here singularity is isolated, and then it's easy to compute monodromy eigenvalues. And I claim that they are 1 and all primitive 65th roots of unity. And so, for instance, yeah, for this example, if you believe all my numerical data, the conjecture is true. Because e to the 2 pi I, these rational numbers, are indeed monodromy eigenvalues. Note that I only have 2 real parts of poles, but I have many eigenvalues, so it's really in one direction. Yeah. Okay. This is just to give you a flavor, if you never saw monodromy, just what kind of mathematics it is. Okay. But where is this coming from? I mean, okay, I stated it as a conjecture, but it's very weird. I mean, why would one make such a link between this number theory, I mean, poles of this rational function pt or Igusa zeta function, this p-adic integral? Why would one make such a link between these poles, just number theory, and these geometric invariant monodromy eigenvalues? It's a bit weird, no? Okay, so let me motivation. Because, yeah, this is, I mean, if you don't know where this is coming from, it's hard to believe why somebody would make such a conjecture. Okay. Well, the motivation is these are the so-called Archimedean zeta functions. The p-adic zeta function, the Igusa zeta function is p-adic, and this is also called non-Archimedean zeta function. So what do I mean? So, okay, let me define some similar integrals. So now I switch. Now I consider f over r or c, depending on your taste, you can choose. You have two versions, over the reals and over the complexes. And I just write down a very similar integral. Well, either over Rn, and I take the usual absolute value, again to some complex parameter, the usual measure, or I take the complex version, I integrate over Cn. Okay, I take 2s, but that's not important, that's just a habit. And then I take dx wedge dx bar. So this is an n form, this is a 2n form. And here I have to add some function phi to make this converge. I will not write it down, I will just say it. Phi is some C infinity function with compact support in order to make the integral converge. So again, S is a complex number with real part of S positive. I'm just adding some C infinity function with compact support to make this integral converge on this region. Yeah? And again, it's holomorphic in this region. So just the same, except for this phi, which was not needed in the p-adic case because Zpn was compact. Yeah, it's just the same. In fact, this is a very old object of study. Did I write it down? Yeah. So in 54, the old Gelfand asked about meromorphic continuation of this function. I told you that in the p-adic version, Igusa proved meromorphic continuation by resolution of singularities and showing that, well, it was rational in p to the minus s. But this is earlier, this is a lot earlier. Yeah? And in fact, at that time, well, it was not known whether this function in S, so let me again denote it, right? So Z, S, okay, maybe that's the phi. It was not known. Gelfand asked, does this function have a meromorphic continuation? And the answer turned out to be yes. And it was shown in different ways. It was shown using same strategy, resolution of singularities. And another strategy using Bernstein polynomials, or so-called B functions. So the resolution of singularity strategy was developed by Bernstein and the younger Gelfand, and independently by Michael Atiyah. And then Bernstein gave another proof using, well, polynomials carrying his name now. So if I remember well from the program, there will be a talk about Bernstein polynomials. I don't remember who is.
Michel Granger will talk about it.
Michel will explain you everything about Bernstein polynomials. Okay. And a byproduct of this proof, for instance, of using resolution of singularities, is that the poles of the meromorphic continuation belong to something similar as in the p-adic case, the negative rational numbers. Okay.
You mean again the real part?
No, good question. This is different. The poles are really rational numbers. In the p-adic case, they can have a non-zero imaginary part, but the real part is a negative rational number. Here they are really zero imaginary part rational numbers. Okay, and this is the theorem motivating the monodromy conjecture. It's a theorem by Kashiwara and Malgrange, Bernard Malgrange. Did I write down the year? Yeah, 83, 84. If some negative rational number is a pole of this Archimedean zeta function, then e to the 2 pi I, this pole, is a monodromy eigenvalue of f. Is a monodromy eigenvalue of f. So okay, this is a, you see 83, 84. This was known, and then Igusa just computed, maybe for fun, some examples of his p-adic version of this thing, and noted that, aha, the poles are monodromy eigenvalues, just as in this classical case. But that's, yeah, the only reason.
So how did Kashiwara and Malgrange discover this relationship?
Well, one way to see this is, well, the Bernstein polynomial technique to prove meromorphic continuation is very natural, in fact, and it is, and there's a nice link between roots of Bernstein polynomials and monodromy. So the Bernstein polynomials are the natural link, in between here. So both arguments are then quite natural, but yeah, the combination of the arguments falls down in the p-adic case. It doesn't work. So I will not give a whole list of people giving partial results. Let me just state the case of two variables, because this monodromy conjecture for the p-adic Igusa integrals, it's proven for polynomials in two variables already a long time ago, for the first time by François Lezer. I don't know if I wrote down the year. Yeah, I wrote down the year. So results n equal 2, so two variables. François Lezer proved it in 1988. In fact, he proved something stronger, and then it was a corollary. But there are some easier proofs later on.
So result was a monodromy conjecture.
Yeah, results for, let's say, p-adic monodromy conjecture. Yeah, poles of the p-adic zeta function gives you a monodromy eigenvalue. Yeah. Okay, Bart Rodriguez has a more elementary proof in 2004. It also follows from more general theory by Nemeti and myself. but the frustrating thing is this is the only case that is really proven up to now. Let me just measure. There are many partial results, many special cases. I will not give you a whole list of names. I did some stuff in dimension 3. But just let me tell you that, well, all the proofs are just working hard. So you can try to study, to describe poles of the p-adic zeta function using resolution of singularities. There is also a formula of Acampo allowing you to study monodromy eigenvalues in terms of resolution of singularities. So that's one classical strategy, using resolution of singularities to describe both sides and then work hard and then with a lot of combinatorics maybe prove something. But this gives no insight. Yeah? The nice thing is that from the proof sometimes you discover new geometric results. That's nice. Yeah, but I will not give examples of that. So if you have, I think one needs a new idea. So challenge, find a new idea to attack the monodromy conjecture. Yeah? Up to now, all proofs are really ad hoc of the special cases.
An 80% not have to make them
Yeah, well, yeah. So it doesn't work. I mean, so the Bernstein polynomial technique is using integration by parts, and it falls down in the p-adic case. Yeah. It's quite conceptual in over R and C, but it doesn't work. So one needs a new idea. Okay, still have a bit of time. Okay, and the last part. So in my abstract I said zeta functions, so there will be more zeta functions. The last ones I want to mention are the Motivic and topological zeta functions. Okay. Maybe on this blackboard I recall the defining integral in the p-adic case, because I want to modify it a bit to motivate definition of Motivic zeta function. So this was integrating over Zpn p-adic absolute value to some complex S. I will rewrite this as follows. What is the p-adic absolute value? Well, that's p to the minus the p order of f, yeah? And then this to the S. That's just definition of p-adic absolute value. That's p to the minus the p order of f. Yeah, you plug in f some set of p-adic numbers. You get some power of p times a unit, and this describes the order. Okay. Now a bit more general. K can be any field, let's say, of characteristic 0. And I take now f over k. And I will define, well, I will not explain all details, but I will define for you a Motivic zeta function with analogy. I take this formula as analogy, as motivation. It was defined by Denef and Leuzer in 98. Let me call it Z mod from Motivic. Okay. Okay, I will write down something weird, but then I try to explain. Bracket of a fine line to the power minus t ord f times, again, some parameter s. I integrate over arc space, and this is some measure. I'm not sure what you saw yesterday about jets and arcs, but I cannot explain everything in detail, but the idea, this is the arc space of affine space. I don't know, there, you saw arcs?
Yes, the jitters.
Other notation?
Yes, A is infinity. But
A and infinity, okay. So the arc space of n-dimensional affine space. Did you see brackets as elements in the Grothendieck ring? Two different answers. Okay, so this is the bracket denotes the class of the affine line in the Grothendieck ring of algebraic varieties over K. Yeah, this is the called T order when you work with jets and arcs. So it's very similar, you see, and this is just the measure. I don't know if you saw the measure on the arc space. It's just the measure on the arc space. So it's completely similar. Yeah? And in fact, Neve and Leuzer prove in the same paper that, well, if you take K, the, let's say, rational numbers, for almost all P, this specializes to the p-adic Igusa set function. Almost all means all except a finite number. So, and in fact, in order to show this, they need some formula in terms of resolution of singularities. So let me give you a formula for this thing in terms of resolution of singularities, and then conclude with the last open problem. Okay. Maybe I fix some notation here. Excuse me. Okay, let me fix some notation because I think it's important that you saw, well, some formula for these things once. Okay, so I have my hypersurface f equals 0 in affine space. I take some embedded resolution, yeah, some ambient space y, and then the inverse image of my hypersurface is a normal crossings divisor. Let me denote the components by EI. Yeah. So that's the inverse image of the hypersurface. Yeah. So this is y. Sorry. So this is a normal crossings divisor. I cannot draw in higher dimension. Okay. Find space. F equals 0. Okay. So I will have to define some numbers associated to the EI. Yeah. So I need to consider the pullback of f. So this is a function on the resolution space y. I consider its divisor. It's supported on the EI, and it comes with natural multiplicities, and I call these Ni. Yeah, the multiplicities of the divisor of the pullback of the function along EI. Only also look at the divisor of the pullback of the standard differential form, dx1 dxn. So the divisor of this pullback is also supported on the EI. An algebraic geometry way of describing this is just a relative canonical divisor, if you prefer. And okay, it comes with some natural coefficients again. And by convention, there's a -1 here, but that's not important. So the Ni and the nu I describe the multiplicities along EI of those two divisors. Yeah. And last notation, I will use a natural stratification of y. Stratification of y. The usual thing you do when you have a normal crossings divisor. For some subset of the index space, I will denote EI with a little circle as the intersection of all EI in the index set minus the union of all the other ones. Well, many people know this notation, but I mean, when I say so there's a natural stratification. Y is the disjoint union of these EI with a little circle. For example, in the two-dimensional case, strata are intersection points, and then the curves minus the intersection points, and Y minus the curves. Yeah, so natural stratification of a space with a normal crossings divisor. Okay, and with this notation, I can give you several closed formulas. So okay. The first one was an old formula of the Neff for the p-adic zeta function, and another one will be a formula of the Neff and Lazare for the Motivic zeta function. This was for the p-adic zeta function. Let me write it down first. So I have this p to the minus n. I have a sum over the strata. To each element of to each stratum, I associate a term, and I just sum everything. So what's the term associated to some stratum here? Okay. I will not explain it in detail, but give you a flavor of what it means. Let me first write it down. This is some complicated number, and then I have the product over the element small I in the index set, and then I have p minus 1 over p to the new I plus ni minus 1. See, the new I and ni are these numbers popping up. Yeah. And what is this? So this was for the p-adic zeta function. Bar means reduction mod p. There's a general construction in algebraic geometry to construct reduction mod p. Then with the bar, this becomes a variety over a finite field with p elements, and I just look at the number of points with coordinates in fp, roughly. Yeah, don't want to say more. And that's okay. When Herwig asked about a closed formula, that's the Neff's closed formula. But you have to be careful. This is only true when the resolution map H satisfies some condition the Neff called good reduction mod P. It's not always. There are some, yeah. And if you start with a polynomial over the integers, you can do this for all but a finite number of primes. Yeah. Okay. Another formula by the Neff-Lazare in the paper where they introduced the Motivic zeta function is completely similar. The Motivic zeta function is, well, you replace P by class of the affine line. This becomes easier. You just take a bracket in the Grothendieck ring, bracket of this variety, so the class in the Grothendieck ring of algebraic varieties, and then some similar product. So you replace P by class of the affine line. Okay. So, okay, and this formula, as you can imagine, is used to show that the p-adic zeta function is a specialization of the Motivic one for almost all p. Okay. Okay. Finally, let's play with this formula to introduce the last zeta function of this morning, at least of this first lecture. Let's look at the p-adic formula. And let's do something funny. So we pretend we are first year students. We are in calculus 1. And we look at this formula, and we will heuristically take the limits for p going to 1. When you go, let prime numbers tend to 1, well, your students in first year calculus, you will fail them probably if they try to do this. But okay, when you're established mathematicians as the Neff and Lazare, you can do it. Okay, they did it. So what does it mean? What does it mean? Let p go to 1 in this formula above. Okay, p becomes 1, that disappears. So you get sum. Okay, you have this complicated thing. I will tell you immediately what the limit is. Let's first look at this product. That's easy, that's the L'Hopital rule. Okay. L'Hopital rule. Why not? What is this? Let me just say it in words. Number of FP points on some variety, EI not with the bar, some variety defined over FP. Well, Grothendieck's trace formula says that number of FP rational points, that's an alternating sum of trace of Frobenius. Yeah, several of you know this. Yeah, number of points over FP. Grothendieck's trace formula says that's alternating sum of traces of Frobenius on cohomology. Okay, what is Frobenius, the p Frobenius when p goes to 1? Well, Frobenius is p's power. When p goes to 1, is identity. Yeah, why not? So the limit of Frobenius going to 1 is identity. So you get alternating sum of traces of the identity. But the alternating sum of Betti numbers. Aha, so this limit is the topological Euler characteristic. Yeah, just topological, I mean by this topological Euler characteristic. Just the usual thing you learn. First Euler characteristic. Okay, so again, probably you fail your students when they tell you this argument, but the Neff and Lezère got a paper in a journal EMS using this argument. Okay, I'm cheating a bit, of course. I mean, they really have some smart tricks to make this argument exact. Yeah? But the point is, after this kind of stupid explanation how you reach this formula, well, maybe it's an interesting invariant. Yeah. And indeed, this is now a definition of the topological zeta function associated to f. F can be, any complex polynomial. Yeah. But it's a definition. We define topological zeta function of f as this formula in terms of some chosen embedded resolution. Okay? And then my weird explanation about letting p go to 1. Well, the Neff and Lezère can make this into a solid argument in their paper that this expression is independent of chosen resolution. Yeah. In fact, you have many arguments now. I mean, you have the original the Neff-Lezère argument. Well, let me write it like this. But, okay, making it more exact. Of course, nowadays you can do it with weak factorization. But at the time of the paper of the Neff and Lezère, there was no weak factorization available. Yeah. And now you can also view it as a specialization of the Motivic one. Specialization of the Motivic one. But okay, anyway. There are many arguments now to see that this is independent of chosen resolution. But and whenever you want to prove something for a p-adic Igusa zeta function or Motivic zeta function, this is a very good test case. It's a lot easier to work with this guy. Yeah, so it's more concrete. So it's a very useful gadget. Okay, and let me conclude with what I would call open problem 3. In fact, the two previous open problems are well-established conjectures or questions. Yeah. The rationality of this series counting numbers of solutions, it's still there. This is an old problem and we don't know how to do it. The monodromy conjecture is now a well-established open problem. This is more kind of personal problem in the sense that some people will say, okay, no, this is not a problem, but I think it's a problem. Give a intrinsic definition of the topological zeta function. What do I mean? The definition is still this, and you have many arguments that's independent of chosen resolution, but I'm not satisfied with this. I mean, I would like to see a definition, some nice, whatever, I don't know how, because otherwise I would not state it as an open problem. Give some definition of this invariant, and then prove using resolution of singularities that this is a concrete formula for it. Yeah? Up to now, well, nobody has given a definition like that. Yeah, we work with topological zeta function with this formula, and this formula is in fact the definition. I mean, it comes from this heuristic stuff from p-adic or Motivic, but you need the formula for the p-adic or the Motivic one to derive it. You need the formula in terms of embedded resolution. So I'm not satisfied with this. So. Okay, many open problems. So thank you.
The fact that it is a specialization of the Motivic Zeta function doesn't.
Well, okay, I gave kind of integral definition. You can also give a formal power series definition, but specializing this somehow doesn't work. It's really, well, probably you know, this p going to 1 weird argument, or l going to 1 in the Motivic case. It's why the variable and the coefficients are simultaneously going to something, and that makes it weird to do something with the definition of the Motivic zeta function. At least there is no natural immediate way to get something from the definition of the Motivic zeta function. That would be a, yeah, that would answer my question. But I hope there is something, but I don't see it.
I would like to see that the generating function of some counting function, for instance.
Yes, but which one? Yeah.
Can't you use the arc spaces?
Yeah, sure. That's the first idea. Yeah. So that's why I add this question here. Yeah. Sure. Maybe by the end of the week somebody tells me something. Yeah. Sure. Arc spaces would be something to try.
You can have a joint publication, 50 people.
Yes.
How are related poles of topological solution?
Good question. Yeah. Well, when you have a pole of the topological one, there's a theorem saying that, well, for infinitely many unramified extensions of base fields, you will have a pole of p-adic Igusa theta function, but then for extension fields. Yeah, it's not that nice, but there is a. You see, this one is a specialization, so it could be that, well, that you have some pole for the p-adic one. So pole meaning that a residue is not zero, but since this is a specialization, maybe in the specialization the residue becomes zero. This can happen. Let's call this an accident. This can happen. Yeah. Yeah. But there is a conceptual result saying that for infinitely many stuff, if you have a pole here, you will have a pole there. Yeah.